This is about as easy as a differential equation gets. Two modes, both decaying, no forcing, no nonlinearity. The answer is smooth and boring. Here is forward Euler solving it, with a time step small enough to resolve everything you can actually see. 50 steps later, the numerical solution is 10 to the 47th. The true answer at that moment is 10 to the minus 261. Nothing is wrong with the code. Nothing is wrong with the equation. The method is doing exactly what it was designed to do. And by the end of this video you will be able to predict this failure before you run it. Stiffness. The reason your solver crawls when the physics doesn't. Two questions get asked about a numerical method, and they are almost always confused with each other. The first is accuracy. How close is my answer to the truth? That one is continuous. Have the time step, have the error, roughly. There is no cliff. The second is stability. Does my answer stay bounded at all? And this one is not continuous. There is a threshold. On one side the solution decays like it should. On the other it grows without limit, and no amount of patience will save it. Watch the time step come down. Nothing improves, and then it works. That is not an accuracy curve. That is a switch. Stiffness is what happens when the switch sits far below where accuracy would have let you stop. Let's build the tool. To understand any of this we need the simplest possible stiff-capable problem, y prime equals lambda y. One mode, one decay rate. Its exact solution is a pure exponential. Forward Euler on this is a single line. And notice what happens when you factor it. The method doesn't produce a complicated recurrence. It produces multiplication by a fixed number. So define z as h times lambda. Not h, not lambda, the product. The time step and the physics only ever appear together, and that is the single most important structural fact in this entire subject. Then the numerical solution after n steps is r of z, to the power n, r is the amplification factor, and for forward Euler it is just 1 plus z. The exact solution decays, so the numerical one must too. Which means the magnitude of r has to be at most 1. That is the whole stability condition. Everything else in this video is a consequence of that one inequality. Order check, while we're here. Expand r minus the true exponential. The leading term is z squared, so forward Euler is first order accurate, which, note, is a completely separate question from whether it is stable. Solve that inequality in the complex plane. The whole left half-plane is physically decaying, every mode here dies out on its own. But the magnitude of 1 plus z, at most 1, that is a disk. Radius 1, centered at minus 1. Every point inside is a stable combination of time step and physics. Every point outside diverges. Forward Euler is stable on a tiny puddle inside an ocean of legitimate physics. Our slow mode, lambda equals minus 1, at h equals 0.01, that z equals minus 0.01. Comfortably inside, barely off the origin. Our fast mode is at z equals minus 10. That is nowhere near the disk. It is 5 diameters away. And to bring it in, the real axis crossing is at z equals minus 2. So h times lambda must be at least minus 2, h at most 2 over the magnitude of lambda. 2 divided by 1,000. 2/1000ths of a second. Accuracy was happy at 5/100ths. Stability demands 2/1000ths. 25 times more work, and every bit of it spent on a mode that contributed nothing to the answer. Real problems are systems, not scalars. But if the matrix is diagonalizable, a change of variables turns the coupled system into n completely independent scalar equations, one per eigenvalue. Each of those is the test equation. Each gets its own z. Each has to sit inside the disk. So a system with n modes is n separate stability questions, asked of the same time step. And here is the trap. The method is stable only if every mode is stable. One point outside the disk is enough to destroy the entire solution, because the modes get mixed back together when you transform home. So the time step is set by the largest eigenvalue magnitude, the fastest mode. But the duration of your simulation is set by the slowest mode, that's the one still changing when everything else has died. The fastest mode picks your step size. The slowest picks how many steps you need. When those two disagree by orders of magnitude, you are in trouble, and the trouble has a name. The stiffness ratio is the largest eigenvalue magnitude over the smallest. It measures exactly the disagreement we just found. I want to be honest about something here, because most treatments aren't. There is no universally agreed definition of stiffness. The ratio is a useful indicator, not a theorem. Nonlinear problems can be stiff with no eigenvalues to speak of, and problems with a large ratio can be perfectly easy if the fast modes are never excited. The definition that actually survives contact with real solvers is behavioral. A problem is stiff when stability forces a time step dramatically smaller than accuracy would require. That is a statement about the method as much as the problem, which is the clue for how to fix it. Let's put a number on this with a wall. 300 millimeters of solid brick, the kind in every older building in the Kathmandu Valley. Conductivity 0.72, density 1920, specific heat 835. That gives a thermal diffusivity of 4.49 times 10 to the minus 7 meters squared per second. Discreteness in space with central differences and leave time continuous. That is the method of lines, and what it hands you is exactly the system we just analyzed, y prime equals oy, with a tridiagonal. At 1 mm spacing that's 299 interior nodes, and the spectrum has a closed form. Here it is, laid on the real axis. The slowest mode has a time constant of 5.6 hours. That is the physics, that's the wall responding to the day-night cycle, and it is the entire reason we're running the simulation. The fastest is minus 1.796 per second. A time constant well under a second, describing temperature wiggles between adjacent millimeters that die before you could measure them. The ratio is 36,000. Now feed that into the stability bound. And look at what that inequality actually is when you substitute the eigenvalue formula. That is the Fourier number condition. Every heat transfer course states it. Almost none of them derive it. It is not a rule of thumb and it is not empirical. It is the point where the fastest eigenvalue of your discretization crosses the edge of forward Euler's stability disk, and nothing more. Which means 24 hours of wall costs 77,600 time steps. To resolve a signal whose period is 1 day. Have the mesh, quarter the time step. 8 times the work for one refinement. 1 character changes. Evaluate the right-hand side at the new time level instead of the old one. Now the unknown appears on both sides, so rearrange. And the amplification factor becomes 1 over 1 minus z. Check the magnitude for any z in the left half plane. If the real part of z is negative, then 1 minus z has magnitude greater than 1, so r has magnitude less than 1. Always. For every time step, however large. That property has a name, astability. The stable region contains the entire left half plane. Every physically decaying mode is numerically stable, unconditionally. The disk is gone. Our fast mode at z equals minus 10 hasn't moved. The stability region moved. Nothing is free, of course. Every step now requires solving a linear system, and for a nonlinear problem, a Newton iteration with a Jacobian inside it. That is genuinely more expensive per step. But for the wall it is a tridiagonal solve, the Thomas algorithm, order n, 299 operations. And it buys us a 5-minute time step, which resolves a diurnal cycle with room to spare. 288 steps instead of 77,600, at a per step cost that is a rounding error. This is not a trade-off. For one-dimensional conduction, implicit simply wins. Understand where that stops being true, though. In 3 dimensions the linear solve is no longer cheap, and if your problem also has a physical timescale as fast as its stiffest mode, a shock, a detonation, then you needed the small step anyway, and implicit buys you nothing. Stiffness is a mismatch between scales. No mismatch, no benefit. One more thing, because this catches people constantly. Crank-Nicolson is second-order accurate where backward Euler is only first. It is also astable. On paper it dominates. Here they are, same stiff mode, same time step. Backward Euler decays straight to zero. Crank-Nicolson rings. Look at what the two amplification factors do as z goes to -infinity, as the mode gets stiffer and stiffer. Backward Euler goes to zero, infinitely stiff modes are annihilated in one step, which is exactly what the physics does. Crank-Nicolson goes to -1. The stiffest modes are not damped at all. They are preserved, and their sign flips every single step. At z equals -10, Crank-Nicolson's factor is -0.67. Stable, the magnitude is under 1 but alternating. That is the ringing you have seen on the first few steps of a stiff Crank-Nicolson run, and it is not a bug in your code. The property backward Euler has and Crank-Nicolson lacks is called L-stability. If your problem has a sharp initial transient, a step change and a boundary condition, a wall hit by sudden sun, take the first few steps with backward Euler, then switch. That is what production solvers actually do. So, stiffness is a scale mismatch, the stability disk explains the Fourier number, and implicit methods trade a solve per step for the freedom to ignore modes that don't matter. Next time, Green's functions.